Hello guys, Seungju here. Today I was pretty bored, so I decided to read some articles that I wanted to read. One of them was Homomorphic Encryption, so this video is going to be about me explaining what I learned about homomorphic encryptions. So let's begin. Homomorphic encryption, as the name suggests, is a type of encryption. And as a lot of people know, there are two categories of encryption system. One of them is symmetrical encryption, where you encrypt and decrypt with one key. Typical example of this is OTP, abbreviation of one-time pad. And there is another method of encryption, which is symmetrical encryption, where you use two keys, which are the private key and the public key to encrypt and decrypt the message. I'm not going to discuss about how they exactly are done, or what type of asymmetrical or symmetrical algorithms they are, because that's not the focus of this video. But I'm mainly going to focus on how homomorphic encryption is done. So the definition of homomorphism, first of all, we have to talk about, is a preserving map between algebraic structures like group or ring or fields that preserve the operation of the structure. The first time I learned about homomorphism was when I was learning about abstract algebra, and I learned in group theory. And the homo is derived from the Greek word of homos, which means the same, and morphe means the shape. So basically, it means that the two algebraic structure, for instance, has to have the same shape in order to be called homomorphism. The mathematical formal definition is as follows. Let x and y, two sets provided with binary operations, the Cartesian product of x equals to x, and the elements of the x and x tilde form a new element which also belongs to x, and it goes same for the y. Then a map f of x to the y is called homomorphism if for all the x and x tilde, the element of x, is f of x operation, like addition or multiplication, x tilde is equal to f of x operation, f of x tilde. So let's go to the next page. Yep. So the definition of homomorphic encryption is pretty similar to what I just explained about homomorphism above. It's basically a special kind of encryption scheme that enables operations like addition or multiplication to be performed on encrypted data, which produced results that matched those of operation on unencrypted data. So the reason why we use homomorphic encryption is that the legacy encryption method poses private concerns, because eventually when you're using the third-party service or cloud service, you're basically sharing your key with them. So this kind of poses a big threat to privacy. However, in terms of homomorphic encryption, you don't really need to worry about it, because what really happens is that, for instance, I draw it here, when the client first of all encrypt the message x, so it is encrypted like this, and it is transferred or sent to the server, the encrypted message, which is the ciphertext, and here they basically compute a function f, this one, on the encrypted message just like I explained in the homomorphism. And this encrypted message, once again, wrapped encrypted message is sent back to the client, and the client then could decrypt this wrapped encrypted message and get the result back. The firmer definition of homomorphic encryption is pretty similar to what we discussed in homomorphism. Let M be the set of all possible messages, and E be the encryption algorithm. E of M1 operation E of M2 is equal to E of M1 operation M2 for all the M1 and M2 elements of M. So it's very similar to what we learned in homomorphism. The homomorphic encryption is characterized by 4 operations, which is key gen, encryption and decryption, and evaluation function. The key gen is the operation that generates the secret and public key for asymmetric version, or single key for the symmetric version. But this key gen and encryption and decryption is commonly found in all other legacy algorithm, but only the eval is an homomorphic encryption specific operation, which takes ciphertext like this as input and output of ciphertext, which is this one, corresponding to a functioned plaintext. So basically, the eval performs the function f of x and over the ciphertext like C1 and C2, for instance, without seeing the message of M1, M2. So the eval function takes the ciphertext as input and output evaluated the new ciphertext, and this could be then transferred to client, and the client could decrypt it and read the message. In this homomorphic encryption that I just drew, the format of the ciphertext after the evaluation process is preserved in order to be decrypted correctly. So I basically made a small kind of drawing to explain how it works. So first of all, in the step 1, the client C, I don't know if you can see, yeah, the client C encrypt his message, the M, and it becomes E and C M, and sends the encrypted data to the cloud server, right? And in step 2, basically when the client wants to perform a function, like query for instance, which is the F, the evaluation function, over his or her own data, he could send the function to the server, right? And step 3, the server performs the homomorphic operation over the encrypted data using the eval function. And in the step 4, the server returns the encrypted result to the client. And finally, the client could recover the data with his secret key and obtain the result of f of m. This was a pretty long kind of explanation of how homomorphic encryption is about. There are more about it. There are actually things that I didn't talk about, like types of homomorphic encryptions. There's a full partially homomorphic encryption. There's a fully homomorphic encryption, which is kind of the newest algorithm. and there's like semi homomorphic encryptions. But if I have time, I might make new videos about this. But for now, this is it. If you have any question, you can leave down in the comment, and peace.